Hello everyone, this is Ying Chen, a graduate master student from Tsinghua University. In this video, I'm going to talk about our work, high-quality live streaming under lower uplink bandwidth, an approach of super-resolution-based video coding. Recently, live streaming has shown unprecedented global growth. A such increase in live streaming services attracts more broadcasters and more active viewers. There are a large number of uploaders and viewers, which shows the high demand for live streaming. Recent studies in live streaming can be divided into two parts, the video uploading side and the video distribution side. The video uploading side concerns the video delivery from broadcasters to cloud servers, and the video distribution side focuses on download link servers improvements. In a live streaming platform, live broadcasters generate their live content with different devices in different network environments. Based on our findings, the upload speed is much slower than the download speed for both fixed broadbands and 4G networks. Also, recent study shows that the required bandwidth to deliver a high-resolution online stream is at least 6 megabits per second, but the average uplink transmission rate of a commercial live streaming servers is less than 1 megabit per second. Therefore, live streaming platforms struggle to provide high quality and low latency live streaming with limited uplink bandwidth. In this work, we propose a novel video uploading framework, Live SRVC, that improves live streaming quality with low latency transmission and limited uplink bandwidth. Here's our system architecture including the broadcaster side and the cloud server side. On the broadcaster side, broadcasters utilize video coding module to encode the captured raw frames based on the bitrate selection and keyframe compression ratio determined by the bitrate adaptation algorithm. At the cloud server side, the cloud servers applied the super-resolution technique to reconstruct the downsampled keyframes in the uploaded live stream and is also responsible for online training of the super-resolution model. Live video is usually encoded into lots of groups of pictures. One group of pictures consists of one keyframe and several non-keyframes. The size of a keyframe is much bigger than the size of non-keyframe. In order to further reduce the video size, we design a keyframe video coding module. On the broadcaster side, raw frames are encoded into a desired bitrate. We extract the keyframe from a group of pictures and downsample it to a lower resolution. We do not downsample non-keyframes to preserve their temporal and spatial characteristics of the high-resolution video. On the smart cloud side, we use the super-resolution model to recover the downsampled keyframe, and we use the upsampled keyframe as a reference frame and encode all frames into high resolution. Our super-resolution-based video coding module can compress keyframes and non-keyframes flexibly according to different network conditions. However, non-keyframe compression involves longer super-resolution process and more computing resource consumption, which affects the overall efficiency. Therefore, in this paper, we only focus on keyframe compression, which is the most cost-effective method since we need to consider bandwidth consumption and computing resources consumption jointly. The figure on the right-hand side shows the compression ratio for 3 different live video types. The overall median compression ratio is between 15% and 52%. Our video coding module introduced an additional process to the conventional video encoding and decoding process in live streaming, but the resulting process delay is extremely low. As you can see from this table, the average additional processing time is under 0.5 seconds. Due to the unique characteristics of live streaming, we cannot obtain all content in advance, and scene switching during live streaming may occur at any time. So we need to learn video features online to train the super-resolution model. The figure on the right-hand side shows the training performance on online gaming. Comparing the three curves, we see that the last option can obtain the highest VMAF score, which means after scene switching, adding a new training dataset with a higher chance to be sampled has the best training performance. One single super-resolution model lacks capability to capture all features of different types of video. To improve super-resolution model performance, we leverage the overfitting property to train the corresponding specific super-resolution model for a live channel. However, the computing resources are limited. We cannot train models for all the videos. Based on our analysis of video popularity, we found that the popularity of live video is highly skewed. A small number of top broadcasters account for the most of the live traffic. Many viewers happen to request the same video content at the same time. The streams of the same uploader has the similar peak popularity. So based on our observations, we can divide live videos into three categories. We only train the specific super-resolution model for the hot channel. This is the video super-resolution result obtained from different super-resolution models. It can be seen that the specific models brings the best visual video quality. We designed a live bitrate adaptation algorithm to choose the most appropriate compression rate and the best encoding bitrate. The objective function of this algorithm is to maximize users' quality of experience and the future quality gain brought by online super-resolution model training. The inputs are the current computing resources status and the estimate network condition. If the live stream requires a video enhancement service, we will send back model training gain periodically. We first evaluate our proposed keyframe video coding module compared to a novel video coding method, BIPP. This method compresses all the non-keyframes of a live video. As we can see from the table, the compression rate obtained by our keyframe video coding module is 10% higher. In order to verify the bandwidth consumption reduced by our proposed video uploading framework, LiveSRVC, we evaluate the bandwidth usage of LiveSRVC normalized to the bandwidth usage of the original live streaming when delivering the same video quality. As we can see, LiveSRVC reduces bandwidth consumption significantly to achieve the same quality as the original method. We compare LiveSRVC with the state-of-the-art video uploading system LiveNAS. Compared to LiveNAS, the inference time of LiveSRVC is much shorter than LiveNAS. When multiple tasks are competing for a GPU resource simultaneously, our proposed uploading framework LiveSRVC seems to operate more efficiently than LiveNAS. We compare LiveSRVC with LiveNAS under various network traces. With the increase in uplink bandwidth, the latency of LiveSRVC reduces greatly, but the latency of LiveNAS is always kept at a high state. The high latency of LiveNAS is due to the super-resolution process of all low-resolution frames in the cloud. We can see that LiveSRVC improves video quality by 4.5% and reduces upload latency by 40.4% on average. It shows that LiveSRVC can provide a good live streaming service under different network environments, especially poor uplink bandwidth. This is the end of our presentations. Thank you for listening.